go on to the first law. In the SI system, these are the only two units we'll use, although you may still come across Fahrenheit in some instances. Okay, now we look at the first law. And I'll first state this. That for a system that undergoes a thermodynamic cycle, the cyclic integral of heat is proportional to cyclic integral of work. So that's the statement we always start with. So we invoked what is the system, we have invoked what is the thermodynamic cycle, which requires us to know that there are many processes, and we have invoked the concept of heat, and we have invoked the concept of work, all of which we learnt in the previous module, and that's why that module is so important. So what this is that cyclic integral of heat is proportional to cyclic integral of work. A quick illustration is that, say a system starts with state 1, goes to state 2, goes to state 3, goes to state 4, goes to state 5, and say finally comes back to state 1. And because it's finally come back to state 1, this system has undergone a thermodynamic cycle. A cycle which includes a process which is 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 1. This could be a gas in a cylinder piston arrangement where you keep, say, expanding it, heating it, contracting it, cooling it, again compressing it, so anything. There is absolutely no restriction on what we do with this, and it comes back to the same state. So in this case, the cyclic integral will mean that cyclic integral of heat, the symbol means that it is for the cycle. This will be integral of heat process 1 to 2 plus integral of heat 2 to 3 plus integral 3 to 4 plus integral 4 to 5 plus integral 5 to 1. That's the meaning of cyclic integral of heat. Any of these could also be 0, that's fine, that's not an issue. And in the same way, we can also write an expression for cyclic integral of work, and this will be 1 to 2 delta W plus 2 to 3 delta W plus 3 to 4 delta W, 4 to 5 delta W plus 5 to 1 delta W. That means for each process we need to calculate the heat and the work. So for this process the associated parameters are the integrals of these, and we'll just develop symbols for these in a few minutes, because this could be a cylinder piston arrangement as I mentioned, or it could be a system where a fluid moves through different elements and comes back to its same position. And that we can see on the picture with the notes. Here is an example of what happens in a refrigerator or an air conditioner. These are elements that I have denoted here, and these are pipes. So this element has gone through this pipe and it's flowing there. We assume that there is no heat transfer, there is no work transfer here. And this we denote as state 1. It goes into a device called an evaporator where a process takes place, where there is heat transfer, something happens to it and comes out at 2. Then this continues and flows into the compressor, which is powered by the motor, and here another process happens to this working substance, and that same element will come out over here. at every state its properties are changing, and so here the state is now denoted by state 3. Then this flows through the pipe into the condenser. Some process happens here, which is in this case heat rejection. The substance comes out and it's now in state 4. It continues moving through this, comes into the expansion valve where it undergoes an expansion, and after this process it attains the same state which it was here when it started the system. So this little element flowed through this entire system and came back to the same point at the same state. If the state were different when it got back, then it would not be a cycle. So if it is the same state when it comes back, then we say that this little element was flowing through all these and executed a thermodynamic cycle. So this is the second way by which a thermodynamic cycle can be realized. And what I just drew on the sheet is a picture of this thing. There were 5 processes there. Here there are 4. We take a cylinder piston arrangement and then we cool it so the piston comes down. Then we put work on it and compress it, and then it comes to this state C. Then you heat it, it comes to state D. Then you allow it to expand on against a force. It comes to state A, which is the same as the starting state A. So this substance here, which was locked in this, which is like a control mass, went through a cycle. In this case, in the second case that we just drew, this was a flow case where the system is continuously, the fluid is moving and executing different processes, and this is also a cycle. So there are 2 ways in which a thermodynamic cycle can be achieved. So this cycle can be done in a control mass approach or a control volume, or this is a non-flow process, and this is a flow type of process. So there are 2 ways that we can execute a thermodynamic cycle, and in each case this has to be valid. So if you just want to apply this equation, we don't know how to do things. There are still so many unknowns left. So we'll work further on this equation and come up with some expressions that will help us in actually getting the relation between heat, work, and what happens in the process, the properties of the substance. That's what we will do. Okay, so the first thing we do is we look at this equation and say, why can I get rid of that proportionality? And we say, okay, in the SI system, there's a proportionality constant, which will be J, which we say is 1. And so the first law statement becomes cyclic integral of heat is equal to cyclic integral of work, and that proportionality is gone now. We are always going to use SI system. So this is inviolable, always true, but it's always true only for a thermodynamic cycle. We still don't know what happens in a process. That means it went from state 1 to state 2, either in a closed system or in a control volume situation. This equation cannot be directly used. So that's what we will do next. We'll work on this equation and try to come up with some expression that tells us what is the expression of the first law for a process. So this is first law for a cycle. Now we look at this statement for a process. And to do that, we will run a small thought process. And we say I make 2 properties of a substance, P1 and P2. And these are independent properties. And if I put any point on this chart, I would know 2 properties, and that would completely specify the state of the system. Okay, so let's say that is state 1 over here and state 2 say over there. And we take this system. So there's a system, it could be anything, it could be flow or it could be a control mass. We take it from 1 to 2 following a certain path. And when we say that we are following a certain path, it means that at every point during the process, the state of the system is known to us. And then we say, since I know the first law for a cycle, what can I do to complete this cycle now? I've only got a process 1 to 2 and say, okay, your process can be a process that goes back and say this was another process by which it completed the cycle. So it went from 1 to 2 along path A and came back 2 to 1 along path B. And in doing so, these two processes, A plus B, they constitute a cycle. And we can write the first law for this, that cyclic integral of heat is equal to cyclic integral of work, which means on this side we have cyclic integral of heat from 1 to 2 along path A plus the integral of delta Q 2 to 1 along path B. So this is the cyclic integral of heat. This has to be equal to cyclic integral along path A of work plus cyclic integral of work 2 to 1 along path B. All we have done is use the expression that we got a few minutes back, and now we are applying it for this cycle, which is consisting of only two processes. There could be more, but that's not very important. So that's one expression we have. So at least we got to the point where we are now talking of the integral of heat or integral of work for a process, but doesn't tell us too much more than that. So now we say that, look, I'll bring this cycle back to state 1 by going another process. A process C, which means that now A plus C constitutes a cycle. And again, we can do the same thing we did for A plus B. So in this case, it will become cyclic integral of A plus C delta Q equal to cyclic integral of A plus C delta W. Earlier we did A plus B, now we are doing it for A plus C. A and C are two processes, and again, like before, we break up this equation and get that integral 1 to 2 along A delta Q plus integral 2 to 1 along C delta Q is equal to integral 1 to 2 along A delta W plus integral 2 to 1 along path C delta W. So we have now two equations. The first one for A plus B, the second one for A plus C. And what we'll do is now, we'll subtract these two equations. And doesn't matter which way we subtract, let's say we get these two terms remain on the left side, integral 2 to 1 along B delta Q minus integral 2 to 1 C delta Q equal to integral 2 to 1 along B delta W minus 2 to 1 along C delta W. And now we just rearrange some terms over here, and it tells us integral 2 to 1 along path B delta Q minus integral delta W 2 to 1 along path B is equal to integral 2 to 1 along path C delta Q minus integral of delta W from 2 to 1 along path C. So if you rearrange these now, the integral limits are same and paths are the same. So we can now write integral 2 to 1 along path B delta Q minus delta W is equal to integral 2 to 1 along path C delta Q minus delta W. And what it tells us that if these two are equal, whether you went along path B or path C or any other path D, E or F or anything like that, this value of this integral will be constant. That's the thing coming out of this little arithmetic. And that's what we will call that this is a constant that does not depend on the path. So this can be put down as an exact change as integral dE. So we are now defining a new term. dE is equal to delta Q minus delta W, or the more common way that we write this expression, delta Q is equal to delta W plus dE. And that is now valid for a process. And what it tells us, heat transfer to a process, that energy is equal to the sum of the work done by the system plus change in something that is we called E. And now we define E as energy of the system. And that's a new property that has come up. So we ask now, what is E? Or before that, let's complete the discussion and say, well, this was an elemental or differential form of the equation. What will it be for a process 1 to 2? We integrate this and say delta Q 1 to 2 is equal to integral delta W 1 to 2 plus integral dE 1 to 2. And the symbols that we will use for this is Q12 W12 plus E2 minus E1. This is the first law statement for a process. It is the most general form. In coming from that cyclic integral of heat equal to cyclic integral of work, we did not make any assumptions. This is always true, and any further statements of this would be of restrictive nature. That means if this is there, then this would be the case. Before we come to that, let's get clarity on what we mean by energy of the system, which is E. And for that, we say that energy of the system is of two parts. One, its internal energy, and then what we may call as the bulk energy. Internal energy is energy internal to the molecule, which is U, and by bulk we mean two types, potential energy and kinetic energy. We will not go into the full derivation of this, but it's given in the notes. We can find that this is equal to potential energy is mass of the system, G into Z, and this is half m its velocity square. So this V is velocity of system. This is elevation of the system. Now velocity requires a reference frame, something we have learnt in school, that if you have an inertial reference frame, which means it is an absolutely stationary reference frame, then you are in the right, doing the right thing. Otherwise, we define a certain reference frame and say, okay, on this earth, This is my reference frame, and relative to that, we will figure out what is happening. This requires a datum, that means some sort of a level from which we measure its elevation. So that's the second one. And in elemental form, this will become then E is equal to du plus dke plus dpe. Both these are properties of the system, so we can write them as exact differentials and not the deltas. And if you want to do it as integrated and get some numbers, then that expression becomes E2 minus E1 is U2 minus U1 plus half m V2 square minus V1 square plus mg Z2 minus Z1. So this is a very important step. And we should be very clear that when we are writing the first law for the process, the expression is that it is dE and not du. And quite often we see at the very starting point, people will say this is equal to du, which we will say, well, when is that true? For that to be true, this term has to be 0, this term has to be 0. That means if and only if V1 is equal to V2, that means the velocities in the two states are equal and their elevations remain unchanged, then E2 minus E1 is equal to U2 minus U1, and then the first law statement is in elemental form, it becomes delta Q is equal to delta W plus du, or Q12 is equal to W12 plus U2 minus U1. So this is a restrictive condition that only if this is true, then this and this, they are true. If we cannot justify these, then we cannot use this equation. We have to go back and work with E2 minus E1. But there is something here which is nice for us, that we defined U2 and U1, or the U, as energy internal to the structure of the molecule. And that's what we call internal energy. And this is a property of the system. When we say system, we actually mean the working substance which is there in the system. And per unit mass, we define that as specific internal energy as U, which is U divided by the mass of the system. So that brings us to a point where we now start talking of properties, of which we already knew that we have something called pressure. We also saw what the units were in SI system. Temperature, we got an idea of that and little scientific basis for it. We had already come across specific volume, meter cube per kg, which is the inverse of density, kg per meter cube. And now we have added a fourth to the list, specific internal energy, whose units would be like this is energy, this is mass, joules per kg. So if a system has 4 properties, to completely specify the state, how much do we need to specify? Do we underspecify? Then we don't have enough information. We overspecify, then there's a probability that there could be contradictions. And that goes back to our basic idea that to completely specify the state, we need to specify 2 independent properties. This word will become clear a little later in the third module. Well, except for some cases, but those happen to be very important situations, these are all independent properties. So if you take a system and say, I know P and T, except those few cases, you can say, yes, I have completely specified the state, which means that with this information, I can get this, I can get this. Or if somebody says, I know what is T and V is always a unique combination, the state is fully specified. We can calculate P, we can compute U, and anything else. If V and U are given, then also the state is completely specified. We can go back and get P, T, and everything else that we want. So any 2 of these, except for some cases P and T, these are all independent properties. They form a pair of independent properties, and the state can be completely specified. Okay, so that was the idea of eternal energy. And we now look at one case and see how this thing plays itself out. And the example we'll take is a cylinder piston arrangement. So we have some substance inside this, and we are working with an ideal case where there is no friction between this, and there is no leakage between this and this. These are idealizations. In the real world, that's not the case. And when one actually does the engineering of any such machine, you have to factor those things in and say, okay, that much more losses will always be there. So we say that this was the initial state, state 1. And in state 1, the system was at P1, T1, and its volume was V1. And we say that this system is insulated perfectly. Perfect insulation means that there is no heat transfer taking place from this to the surroundings or from here to there also. The piston is also insulated. And this is compressed, pushed down, and the piston comes here. This is state 2. Earlier we had here there was state 1. And now in state 2, we have P2, T2, and V2. We are not putting any restrictions on how it happened, how fast it happened, or anything like that. And we say, let's apply the first law of thermodynamics to this process. The process is 1 to 2. This is a closed system. If we now begin analysis, our first step is to decide what is the system boundary. At state 1, this was the system boundary. At state 2, this is the system boundary. Whatever mass was there in state 1 is still there in state 2. And so we are justified and saying that first, this is a closed system, and we'll apply the control mass approach to this. And for this, we already have the first law with us, which says that Q12 is equal to W12 plus E2 minus E1. We then look at the system and say, look, the CG of this gas was here, now it is here, this is very, very small, there is hardly any change there. This system, whole system was stationary, it is still stationary here, so V1, V2 are both 0. So we can justifiably say that this is equal to U2 minus U1. And since this was perfectly insulated, Q12 becomes 0, and we are left with W12 is equal to plus u2 minus u1 is equal to 0. And now we say, how can I express the work done? So initially this was P1, and we say that when it was up here and it moved a small distance down there, it would be P dV, and we would integrate it over that small element. And then as it went from 1 to the small element A, then it went from A to B, we would do the same thing, and we keep doing that until it finally gets from something, it reaches 2. So that will be lots of small steps that we would take to compute the work output or the work input. And by the way, this is what people do in modern programs that do simulation of, say, an internal combustion engine. That's how one does the analysis. And let's make a simplification here. Let's say that in this compression process, we have done it in such a way that P is constant. And it need not even be necessary that this be insulated. We can leave that in general and say, okay, this is Q12, and this is P is constant, means this will become P integral dV state 1 to 2 plus U2 minus U1, which will be P times V2 minus V1 plus U2 minus U1. Why we are doing this will become clear in a minute. It's not the answer is all that. So this becomes PV2 minus PV1 plus U2 minus U1. And if P1 and P2 are equal, we can quite generally say that this is this minus P1 V1 plus U2 minus U1. And this gives us a term U2 plus P2 V2 minus U1 plus P1 V1. And what we see is a combination coming here, and that's what we were trying to do. U plus PV, U plus PV. And this combination we define as a new property, which is called the enthalpy. H defined as U plus PV. Or in terms of specific enthalpy, H is equal to U plus PV. Okay, so these are relations which are important by themselves, and also in solving many problems, as we will see in a little while, H becomes far more frequent than U. And so if we look for property data, we would be more interested in data for H rather than data for U. Okay, the first thing is units. U is joules per kg. H will also be joules per kg. PV should also be joules per kg. And to get that, P has to be in Pascal and V has to be meter cube per kg. It is important to keep the unit straight when making this calculation. We often work with kilopascals and bar and megapascals, but when we come to this point, we have to have Pascal over there. Next thing is we came to this expression through a little bit of jugglery. We assumed that pressure is constant and then we substituted the initial and final pressures, but that doesn't matter in the end, because what you have is that U, P, V are all intensive properties. That means a property that depends only on the state of the system and not how it got there. So H is also an intensive property. We will look at this in the third module in detail, but for right now, it doesn't matter whether the substance was in liquid phase, vapor phase, solid phase, a mixture or an ideal gas. It makes absolutely no difference. This expression is always true, and so are the other two expressions that we have written for the first law statement. They are completely independent of the application, they're completely independent of the working substance and any pressure and temperature that may be there. There's no issue of having a doubt on that part. Everything else one does in solving a problem is look at special cases by removing something, adding something, and making life a little more easy. So we have now defined yet another property, and if we go back to that sheet where we wrote all these properties, then here we now add to this list one more thing, H, and this is also joules per kg. And like before, if we know any two of these, or even these two, or these two, the state is completely specified and we can calculate the remaining properties. That is what is important, that if you have these two properties, other properties can be obtained, or there are data or charts or computer programs. From there we can get this. And the reason for that is that all these properties are related to each other through differential equations. In this course, we don't have to go into the details of those differential equations. That is the subject of an advanced course in thermodynamics. But using those differential equations, if we know two properties, we can do a mathematical operation and get all the other properties. That's the idea. So we now have that many properties to work with.